Hello and welcome to this video on what are parameter constraints in factor analysis and structural equation modeling. My name is Geiser. I'm an instructor and statistical consultant with QuantFish, and on this channel I present weekly statistics tutorials. I usually talk about multivariate methods including factor analysis, structural equation modeling, multi-level analysis and latent class modeling. If this is something that interests you, please subscribe to this channel. Also, check out the description for additional resources, including workshops that I offer through QuantFish. In this video, I want to explain the concept of parameter constraints. So, what are parameter constraints? When would you use them? What does it look like in practice when you estimate a factor analysis model or a structural equation model? Or also the same concept applies in latent class modeling when you have a latent class model and you place certain parameter constraints. That's also something that is possible there. So here I'm going to focus on factor analysis though, so that we can keep things simple. And so let's get started with the first type of parameter constraint. So the first type of constraint that we have in factor models and structural equation models are fixed parameters. So this means those are parameters in our model that we do not estimate. And there's one very prototypical example when you have a factor model or a structural equation model with multiple indicators for a given factor or multiple factors. Then in models like this, we typically fix one factor loading per factor, usually to 1, for identification. Or alternatively, we fix the variance of the factor to 1 for identification. And so this is an example of a constraint where a parameter is not estimated but is fixed to a pre-specified value. Why is this done? This is done because the metric of a latent variable is arbitrary, so it is not clear in which units we should measure a latent variable beforehand. That's arbitrary in a way, and we can pick one of our indicators to scale the latent variable, or we can scale the latent variable directly by fixing its variance. And so this is a necessity, so to say, to define the factor metric in one way or another. Another example of a fixed parameter is something that's less technical, so to say, but rather is hypothesis driven in terms of us wanting to test a specific hypothesis. So one hypothesis, for example, could be that the covariance between factor F1 and factor F2 in this model is 0.5 in the population. So we might have a specific hypothesis about that, maybe from prior research, or we want to test whether in a given sample we find the same correlation or covariance that was found previously in a different population. And so then we can test a specific hypothesis about a specific parameter value by fixing that parameter to, for example, 0.5, if that's our hypothesized population value. And then we can look at the fit of the model and we can see whether the model with this constraint, with this fixed parameter, is rejected by a goodness of fit test or not. And so then this can be used for testing specific hypotheses. Now, this is relatively rare because oftentimes or usually we don't have hypotheses that are so specific about parameter values so that we would know exactly, oh, this covariance in the population should be exactly 0.5. So usually our theories in the social sciences are not that good, not that strong that we can test exact parameter values, but sometimes this may be the case in some certain circumstances. From prior theory or prior studies, we might have very specific hypotheses about parameter values that we can then test by constraining, by fixing parameters to specific values. Maybe more common than that are equality constraints. So equality constraints are different in that they don't involve fixations of parameters to specific values. So this means with an equality constraint, we wouldn't say this loading is fixed to 1 or this covariance is fixed to 0.5, but rather we would say these parameters should be estimated to the same value. And an example in this factor model here are the loadings lambda 2 of the second indicator on each factor, which you can see here. So you can see that these lambdas have the same subscript 2, so they don't have another subscript, and that indicates that they are constrained to the same value, although the specific value has not been set, meaning we don't fix that loading. We don't fix it to 1 or any other value. We just simply tell the structural equation modeling program this parameter for y21, this loading for y21 should be estimated to the same value as the loading for y22, whatever that loading may be, but it's supposed to be the same value. And I'll show you an example on the next or on one of the following slides here. So equality constraints are less specific, so to say, and therefore used more frequently because it doesn't require us to know exactly what lambda 2 should be for both these variables, but rather we're only assuming that they have the same loading. When would you assume something like that? For example, you could assume this if this represented a longitudinal confirmatory factor model, meaning where y11 and y21 are the same variables as y12 and y22, but measured on 2 different time points, where the factor f1 represents your construct or latent variable at time 1, and f2 represents the same construct at time 2. Let's say, for example, intelligence or anxiety or something like that. And so you want to measure changes across time or the stability across time in your construct. And then oftentimes we assume measurement invariance or measurement equivalence. And that involves having equal loadings across time in addition to other parameters such as intercepts and potentially error variances that also then are tested for equivalence or equality across time. And so in a longitudinal confirmatory factor analysis model, we would typically test for equivalence of the loadings of a given indicator across time. For the first indicator here, this would already be set because the loading is fixed at 1 at both time points, so that then also implies equality. But the second loading would be estimated, and then in order to test for it to be, or test whether it's equal across time, we would set it equal. So we would impose an equality constraint on that loading lambda 2 for measurement invariance of the loading. That's one example. This is also common in multi-group analysis when you have the same factors in different groups or different populations, and you want to test for measurement equivalence or invariance across groups. And I have separate videos and a whole playlist on the topic of measurement invariance. If you're interested in that, you can check that out as well. So that's where that's common to have equality constraints. Now let's take a look at an example. So here I'm using Mplus for setting up a model with 2 factors and with the loadings constrained in that same way that I showed you on the previous slide, as well as the covariance here constrained. And so you can see that in Mplus we're using the at symbol to fix a parameter. So here the first loading is fixed at 1, and in fact Mplus would do that by default for each factor. So the first variable that is listed after the by statement in Mplus is always by default fixed to 1, that factor loading. So we wouldn't even have to tell Mplus that this loading should be fixed, because Mplus knows that there has to be a constraint imposed in order to identify the factor metric, and it uses the loading constraint as the default method. The second factor loading and subsequent factor loadings would normally be estimated freely, and so here in Mplus we are constraining the second loading equal across factors by giving it the same parameter label, and a parameter label in Mplus is given with parentheses, so a number or label with words or letters can be used. So here I just used the number 2 for the second loading, and so since I'm giving the same number 2 here assigning the same one to the loading lambda 2 for y22, this loading will be set equal across factors. And then also you can see I have a command here for the covariance f1 with f2, and this was fixed to 0.5 for this example. So this would allow me to test the constraint that the covariance between f1 and f2 is 0.5 in the population. Now, in terms of the output, what is important to know is that a fixed parameter has no standard error. So you can see that here the first loading on each factor, so here for y11 and also for y12, which is fixed exactly to 1, has a standard error of 0, and in Mplus gets these 999 scores for the test statistic, the estimate divided by its standard error, which is a z statistic for a test of significance, and then also the p-value is also 999, which means NA basically. And so this is always the case. When you have a fixed parameter, that fixed parameter will not get a standard error or a test of significance because the parameter is not estimated. And when something is not estimated, then there will be an uncertainty, a standard error, to quantify the degree of uncertainty with which this parameter is estimated. And so this is something then that is important to know. A fixed parameter doesn't come with a standard error or a test statistic, whereas a parameter that is constrained equal does come with a standard error and a test statistic, as you can see here from the second loading, which is estimated to be 1.012 for both variables, y21 and y22, and it gets the same standard error, 0.042, because it is estimated only once. So in contrast to a fixed parameter, which is not estimated at all, a parameter that's constrained equal across multiple variables is estimated once. So you're still using up a degree of freedom for a parameter that is constrained equal, whereas you're not using up a degree of freedom for a fixed parameter. That's also important to know. And so you can see that when a parameter is set equal, then it's estimated only once, and it gets one and only one standard error, one and only one test statistic. Here the test statistic is z equals 24.337, which is a very, very large z-score that is statistically significant, showing that this loading is statistically different from 0 or significantly different from 0. So that's what that looks like when you have constrained parameters in terms of their standard errors and test statistics. Now, at the end of this video, I want to talk about when you would actually use parameter constraints. So when in practice is this something that we employ? And so first, as we discussed at the beginning, we need parameter constraints for model identification and for setting the metric of our latent variables, because latent variables are arbitrary in terms of their scale, in terms of their units of measurement. It's not clear, so to say, what scale they should be measured on, and therefore we need certain fixations in order to set the scale of the factor. And again, this is typically done by fixing one factor loading to 1 or by fixing the factor variance directly to 1. And then you have the factor scale identified. So that's one area where parameter constraints are routinely used, and in fact that is the case probably in all confirmatory factor analysis and structural equation models, that you have certain parameter constraints that are related to model identification. Next, we saw that parameter constraints can also play a role in hypothesis testing, and here especially in the area of measurement invariance testing, we employ typically equality constraints. That is something that is relevant in longitudinal studies when you have multiple indicator models and you have multiple time points and you want to figure out whether your measures show the same psychometric properties across time, whether there's invariance of the loadings, invariance of intercepts, and or of error variances across time. Also in multi-group analysis, we usually test equality constraints to find out whether groups differ in terms of their measurement parameters and also in terms of structural parameters. So oftentimes in multi-group analysis, we're interested in mean differences on the latent factors across groups, and then we have certain constraints that help us identify a latent mean structure so that we can compare latent means across groups. And that also plays a role in longitudinal studies when we're interested in mean changes across time, where this follows the same principle. And then finally, we have constraints in special models, for example, in latent growth curve models for longitudinal data, when we want to test specific hypotheses about the form of change across time. So for example, in linear growth curve models, all factor loadings are fixed in a certain way. So you have an intercept factor where all loadings are fixed to 1, and then you have a slope factor where the loadings are fixed according to a linear trajectory across time, so that growth is assumed to be linear for all individuals, and then that can be tested as a hypothesis whether a linear growth curve model represents the data well. So that's another example where we use parameter constraints when we have special types of structural equation models that constrain the data in specific ways. I hope you found this video useful to learn more about parameter constraints in factor analysis and structural equation modeling. Don't forget to subscribe to this channel and to check out the description for additional resources, including additional videos that address some of the models that I mentioned here, and I'll see you next time.